Right, okay. I think everything is running. So, we're back. I have, for once, I have a plan of things to do on stream at some point. So I'm just going to be doing that. I think what I'm going to do. Oh, hold on. The title for this is still the one for last stream. That is to say, Sapling livestreams 5. And I don't have all that much time today, so I think I'm probably only going to implement deleting code. I think that's all. Right. Cool. I need to pop out the chat so I can see it. Where's chat gone? Here we go. Right, okay. So pretty much the idea, what we're aiming for, so if we run Sapling as it stands right now, we can move around quite nicely, and we can insert on both sides of anything. So we can say insert an array above the cursor, or insert after the cursor, and both will work. However, what we can't do, we can only insert things. We can insert, and we can replace as well. So we can say like R for replace, and replace true with an array, rather than inserting to either side. But what we still can't do is we can't delete, which is kind of pretty fundamental. Like, it's one of the core things, just the last of the core things that you want an editor to be able to do. So we need to implement that. And I don't think that will be too difficult, although everything seems less difficult before you start doing it, so I have no idea about that. I'm pretty sure, oh yeah, let's have bigger code for everyone. This can be a lot bigger. Is that, okay, that's much more visible, that's good. So pretty much, since the last stream, I went ahead and removed editable tree. There used to be a trait here that said what it was like, what a structure had to do in order to be an editable tree, right? And that was kind of annoying me, because there was only one thing that ever implemented that, which was dag here, which is a thing that stores the nodes stores lots of trees as directed acyclic graphs. So it kind of, whenever you make an edit, instead of completely cloning the tree to say, oh yeah, here's the first tree, here's the second one, other way around for you, here's the first one, here's the second one, it would instead keep all of the branches of the trees that we haven't changed and only rewire the bits that we had. So we would end up with, if I change, oh, is that not what my shortcut is? Okay, well, this worked anyway. So if we change to the drawing thing, imagine we just had an array as the root. So we have root, and we're going to call this root number 1. That's terrible. Let's do that again. You know what? I'm just going to call it 1. I can actually draw that vaguely. And then let's say we had true. I'll just represent that with t, and then false maybe, and then false. In fact, I'll want to give this more space. Or rather, I will want to have more space. So imagine we have true, false, and then false. Okay. Let's get a nice drawing. Okay, so this is one tree. And you can imagine a scenario where I wanted to replace this false with a true. And one way of doing that, you'd have to navigate the cursor down here. And one way to do that would be, well, we need to keep this tree around because we need to have something to undo back to. The only way you can implement undo is to, in a tree-based editor, by far the easiest way is to store some form of multiple trees. On the basis that a lot of them will be similar because you're editing the same file. It makes sense that you can avoid a lot of duplication. So the naive way of doing it, I'll make a new layer for this. There. So the naive approach is we change false to true, and then we need to keep the save state around. So we build an entirely new tree. And so we clone everything. This is true. Oops. This is like the second thing in our history. Can I make that look better? No. So we've got one tree in our history, and then we've got another one, and this is, we've cloned everything, so it initially starts the same. It's true, false, false. And then we make the edit that we wanted, which is to turn this into true. And in general, we could replace, instead of having true and false here, let's make this a bit less childlike. We could imagine a scenario where instead of this, we have just, what? Okay, so instead of true and false, we have just arbitrary trees. Can I rub this out? Not really. Okay. However, I can draw a white on the top of them. That will work. So in this scenario, let's call the trees A. Oh wait, I'm drawing in white. That's why it's not working. So we can say A and B. Oh, I didn't mean it to be that bold. 3. And then down here, we'd also have trees A and B. Did I draw something? No, I didn't. So we'd also have trees A, big A, and big B. Okay, and these trees could be really big, right? There could be loads of stuff underneath here. And by doing this, every time you make an edit, you have to store an entirely new copy of the tree, which is guaranteed to be correct. It has the nice feature that it's really easy to prove. It's really easy to see that this is working. This is really obviously the same tree as we've got here. But it's not very efficient. And so what we have instead, that's what was happening. Okay, let's have a new layer for this. So this is the naive approach, which we're not going to implement because this is very, very memory inefficient. Because A and B exist twice, and every time we would make an edit, if we replace this again, then A and B would exist even more times. So instead, what Sapling does is that we create a new root. Oops. So we create, and this is a new array, and we label this 2. And A is the same. We don't bother with that. So we label A, and B is also the same. So we wire that up. The only thing that's happened is that between A and B, we've changed false to true. Okay, so we end up with a situation like this. And then if we did it again, we'd end up wiring another thing with a third possible thing in between A and B. And this way, you kind of don't pay for the memory space of the thing you haven't edited. So long as we keep A the same, we'll only store one copy of A for as long as A is in existence. Which is why this is called, which is why the node storage is called DAG, because this forms a directed graph because things have children. Like there's a direction to all of the connections, and you obviously can't have a cycle in here because there's no way you could have like dependencies coming down and then suddenly they own the root as their child. That's just like really pathological. There's no way that could happen. One of the things I want to be able to do, which is if we implement delete, that will be the thing we do after this, is to be able to export the entire state of DAG, because at the moment it's really difficult to debug. You can't like see this happening. So it'd be quite nice to be able to export that and get a full tree picture of what Sapling's actually doing. But for the time being, we're going to, first of all, we're going to implement deletion. Can I get to IDE view? I can. Nice. Right. So editing deletion, we've already got the rest of our editing functions there here. We've got a utility function for finishing an edit. For this shouldn't be public. First thing. And then we've got replacing cursor, inserting child, and then inserting next to the cursor. And now we're on to display methods. What I'm quickly going to do is we're going to just check out new branch, and we'll call it implement. Let's call it delete. And what's this? Okay. So Git's just telling us that we changed the tree. I'm fairly sure we changed some files, and it was only making that not public. I'm fairly sure if we do git diff. Yeah, so it's saying I removed the pub from that function. So deleting, I think, is going to be relatively straightforward. It's going to be similar to inserting next to the cursor, in that the node that gets changed, we're not affecting any of the nodes directly, except the parent of the node where the cursor is. So we need the we need a slightly more complicated code to do that. If I switch back to the drawing, what we can imagine with us doing, suppose we have a more complicated tree now. Suppose we have a new layer, and let's make it white. So a completely new drawing. Suppose we have the root, it's an array, and then we have maybe some just arbitrary tree here. And then we have another array. Then we have some children. They could be trees, so let's just call them B. And now we have something here, and this is where our cursor is. And I'm not going to try writing anything longer than single letters. It will just not look very good. Oh, we're on D now. Imagine me knowing the alphabet. Okay, so E. And it's just imagine we have this tree set up. And this is our root. And one of the... Let's get that looking vaguely nice. Okay, so one of the things about Sapling is that the way nodes are stored, they're stored immutably. Once you create a new node and commit it in a sense to being inside a tree, once you make a change, those nodes can't be changed again. So I couldn't replace true with false by just directly overwriting this memory. Rust won't allow me to do that. Instead, suppose I wanted to delete this, as an example. I want to somehow get rid of it and merge these, but I can't, because doing so would require me to edit the parent, because the parent, we need to change who the children of this parent are. And the parent is immutable because it's stored in our big data structure that stores nodes. And all we have is an immutable reference to it. We can't change that. So what we do instead is we just clone this. So we say, make 2 copies of it. Now we've got 2 copies. It's a kind of shallow clone, so it's still referring to B and C. But crucially, we get so it's also a clone, so it will refer to the middle child. Let's make that prettier. We'll refer to T. And then we can mutate this, because this is not part of the tree anymore. So we can just remove the pointer. So now we can create a new thing, which is exactly the same as this, but the node that we wanted to delete is missing. And then we just do the classic thing, like, oh, we want to swap replace this node with the new copy of it, which is this. We can't do that because it's immutable, so what do? We keep going. We clone this node into another one, which has a, and then I'm just going to make some really wiggly lines here. And then the second child, we're going to overwrite. Like initially, it will point here, right? Because we just completely cloned it. But we don't want that. We want it to be here. And now this is our next edit. So this is the node 2. And now we can undo really easily by just switching between these. Like our undo history is just a list of pointers into like root nodes of trees. This diagram looks pretty messy, right? But what it's doing is essentially pretty simple. We can't modify the tree directly, so everything we would need to edit, we have to clone. But specifically, we haven't modified. What's the redo? There we go. We haven't modified true at all. The node under the cursor, we haven't modified it. It's still there. It's just not in the tree anymore. Also, we can't remove it from memory because we might need to undo and get it again. So the edit actually happens to the parent. So the overall effect is we created a new copy of this, and then we modified this. And everything else is just straight cloning with child updates. And that's what, this could happen like arbitrarily far. We could have many more things going upwards. And that would be fine. We just keep on going, tracking which child we changed and then updating it. And then we get an exact copy. And that's what the utility function that we wrote does. If I cheekily switch, okay, it worked. If we go for finish edit, then that's essentially what this is doing. It's fixing the history bug. It's allocating. It's putting the node that the new node in this case. This was. Can you see my cursor? Okay, you can. So what it's saying is that we've just created the parent in this case, and that's not in the tree yet. There's a big data structure that owns all of the nodes, but we've just kind of created that. It is just in the ether somewhere. And in order to make it part of a tree, we can only have nodes in Sapling. Nodes that we're editing have to be stored in the central data structure, because that makes it easy to verify when nodes are in existence and when they're not. We've essentially created a new node that's off the radar. So the first thing it does is adds essentially this node to the tree, which is what's happening here. It allocates new node into the arena. And then what we get back here, this is node, the variable node, is an immutable reference. So now we can't modify new node anymore, but that's okay because we assume that whoever's edit we're finishing has modified it. And then what we're doing here is we're just stepping all the way back up the tree. We can see the iterator, we take an iterator of going down the tree, reverse it, and then we step up, matching the child index, and then we just update the required reference. And then we keep going until there's nothing left to clone, and therefore we've reached the root. And then once we've reached the root, the value stored in node is going to be the new root. So we add that to the root history and move the history to make sure that we say that the current contents of the tree is right at the end of the history. How many viewers have we got? Oh, we got 4. That's nice. I just wanted to check that the stream was running, not specifically check how many viewers I have. So right, now we know what we're trying to implement. We need to but we need to actually implement delete. So let's make a new function and let's call it delete cursor. Eventually, it would be nice to have something that a way of deleting more things at the same time. But for the time being, we're just going to delete the cursor, and we're going to return some result. If it succeeds, we won't do anything. Otherwise, let's just. Do we even need a result? Like, okay, for the time being, we're not going to return a result. It's because the function might not fail. So the first thing we are going to do is we're going to need to know a pointer to every node down to the child. Oh, you couldn't see the code. Okay. So essentially, we have the cursor pointing here, but we don't store any pointers to the other nodes. So we're going to need a list of what we're going to clone. We want to know, oh yeah, the root is here. Then the next element down is this one. Then the next final one is the cursor. So we need to know whatever this array is going to be. How would I draw an array? Let's draw it like that. So we need to know this, and before we can know which nodes to edit. So that's what we do. Quickly switch over. Nice. So what I did when you couldn't see was I just created this, which is just an empty function that deletes the cursor. Well, that says it will delete the cursor. So what we're going to do is we're going to do exactly the same thing we did for this, which is to just get a list of nodes that we're going to have to clone. And then we are doing the same thing because we don't want to take the cursor is kind of irrelevant to us, right? We just want to pop the bottom value, because nodes to clone, the way we're finding this out is we're running down the path to the cursor and then getting an iterator over every node, and that will include the cursor. Like the last thing in that thing is the cursor, but as we pointed out, we can't modify the cursor. We're only modifying the parent's cursor. So we just take the cursor off the end of that list, and then we're left with the parent. We do, however, still need to know which index the cursor was. Where is this? We do find it. Cursor sibling index. Here we go. This is the same. At some point, I would refactor out a whole load of this stuff. Into, like, there's loads and loads of duplication, so we don't really need to do this. What we do want to do is we want to clone the parent. So we want to do something like cloned. I realize it must be very difficult to see what's going on if I'm not actually typing, right? Because if I copy and paste a load of code, then you guys are hard pressed to see what's going on. So what we do, what we want to know is the last node to clone. So we pop that off. We unwrap because pop might fail, but we know there's got to be something in it because it might be the root. And we unwrap and then we clone. Because nodes to clone it's an array of pointers, and we can't just arbitrarily clone. We can't just try and modify the thing at the end of the pointer, because it's a memory. It's inside the arena where we allocate everything, and everything inside the arena is immutable. So we have to clone it, and then what do we want to do? Well, we want to remove the current child. So we want to remove the reference in the children that points to the cursor. So that's the same as saying cloned parent dot children mute. So we get a mutable list of the children. And this is okay because when we cloned it, we now own. We're saying, oh yeah, I own the cloned parent. I can do what I want to it until I commit it back into the arena. So what do we want to do? Well, we want to say, where's the cursor? We want to remove, hold on, what? Oh, this is a slice. Okay, I see what's going on. So the issue is that children mute is returning a slice, and a slice is like a section of memory, right? It has a fixed length. That's the important thing. So you can't actually remove out of a slice, because doing that is like weird, because someone's giving you a slice of a certain length and you're removing something from it. That makes the slice shorter. Like, how does that make sense? So it's not possible, and I don't want children mute to know what the like which children it has, right? Because children mute might have what am I trying to say? Okay, so we might have something like true, which has no children at all, and therefore it returns an empty slice to say, oh, I don't have any children. In fact, that's a bad example. A better example is the field. So in Sapling, let's say we have a field, which is the like colon. It's a key value pair in an object, and key value pairs have to have two children. They have to have a key and a value. There's no avoiding that. So it would be an error to delete the key. You shouldn't be able to do that. And so it should be up to the parent to say, hey, I don't have any, like, you can't change how many children I have, because I have to have two. It's not possible otherwise. So here we need a custom function. We need to be able to pass responsibility to the node in question and say, hey, Mr. Node, I need you to give me, like, I need you to remove a child. And then it's up to the node to say, oh, I can't do this. I'm not allowed to delete that. I'm a field in this case. You can't delete the key. So we need to add that here. Where is children mute? Okay. We want to be able to delete, or let's say just remove child. And actually this won't do anything, so we just need to say @mute self. We need to be able to mutate the memory, the thing, and it's going to return a result that's either something or it's an error. To say, for example, we're trying to delete it, like we could somehow get the code into a state where it tries to call remove child on a constant value like true, which doesn't have any children. You can't delete a child, that's obvious. Or we're trying to remove a value from a field. Either way, we need to return some error. So I'm just going to create a new custom type that anything implementing this. So this trait is what the trait. It's a trait of what it is to be a node in a syntax tree. So this removes. We do need an index though. So index usize. Removes the child at a given index from the children of this node, if possible. And the if possible bit is important, because the whole point of having being able to return an error is that we might not be able to for whatever reason. For example, like the index might not correspond to a valid child, in which case we just can't remove it. So if the removal, was not possible, then we return a custom error type. And then we need to jump up to the thing here, because we already have something for errors in insertions. Error type returned by which function will we return it? It will be AST. It will be insert child, right? And then Oh, I'm hungry. Wow. Hold on. Oh, remove child. Okay. Did I call it delete error? I think I did. Oh well, I can refactor that. And this has to be an error. Yeah. Come on, let me... Okay, fine, it can stay. Most of this will be refactored anyway. So we need to implement this, because that was just saying, oh, we need to add something, some way of deleting things. But now we have to add the required things to the one specific implementation of an syntax tree that we have, which is JSON. And we need to say what a delete error is. We have insert error. Let's not copy it for the sake of stream. I just create a new. I just write comments first. Error type. Actually, I don't want to write a comment first in this case. Oh yeah, let's just basically write it. Error produced when inserting, or when trying to delete a node from a child from this node. And then this is going to be an enum as well. It's going to be called delete error. And for the time being, like, it's pretty obvious there's going to be a way that this can fail, which is fixed child count, which is to say, and this is some string, which is kind of like, what node type is this used for the error message, and then exactly how many children do we have, which is what the two things are going to be here. A child was attempted. Yeah, let's say we attempted to delete a child from a node which must contain a fixed number of children. And we also, did we have a special case for, oh, this is kind of silly, because no possible children is kind of a special case of having a fixed child count. It's just a fixed child count of 0. We could, oh no, I don't have any water. Okay. Never mind. So I'm going to deduplicate it here, and if we have time, before I get too hungry to keep streaming, then I'll deduplicate it in insert error as well. But what we also have is that the index we try to insert in is invalid. So invalid index. Or this is more specifically, it's an out of range. Out of range. And this is string. You can say what's the current node type, and how many children are we going to have, and what the index was. Let's just make a quick comment. We attempted to delete a node child whose index was outside, specifically more than the end, because we're using unsigned numbers. We can't try and delete a negative index, which is just, like, that's a nice check. At least half of the possible errors have disappeared because of typing. We attempted to delete a child whose index was outside the bounds of the child array. Okay, so now we know what to delete. We need to where is the code for inserting child after? Oh, we probably don't. We don't need it. I think. We can just say delete child. So fun delete remove child, and this is going to return delete error, which is kind of bad naming, but I feel like a lot of Sapling is going to be refactored anyway, so that doesn't matter. And this is going to correspond roughly to this. I am going to copy and paste. What I'm copying and pasting is it's pretty much a pattern match of which things can have fixed child count. So true, false, null, and a string has no children in the way Sapling currently implements strings. So this is a fixed child count, and it's inserting a delete error, self.display name, and 0. So if any of these, if you try and remove a child from any of true, false, null, or string, then it's just an immediate error. Same here, except that the typing won't work out. So we need to say delete error rather than insert. If we have an object, then provided the index is valid, so we say if let some that's the side effect of formatting your code. What we need to say is if the index is valid, so if it's less than the length of the child array, so self.children.len. Is that a condition? Yes, that is the right condition. If it is that, then we remove. So I believe there's children mute. We still can't do that. However, we do know self.children is the same as fields, so we're going to do the accesses directly, because the thing contained inside the brackets, fields here, is a vector. So it's not a slice specifically. It owns it owns the stuff stored in it, whereas a slice is someone else's like borrowing. It's just like looking at the contents, and we need to be able to own the contents in order to be able to remove. So there should be just remove. Is remove item. Oh no, so we want to remove at an index, and that index is the index that was passed down. And in this case, we want to return OK. If this were to fail, then we need to return an error to say it's a delete error, and index out of range, self.display name. How many things did we have? Well, it's fields.len, and we tried to access index. Excuse me. What? Oh, the comma's not right. Okay. And the code for array is basically the same, right? Because an array, we don't have to do any type checking, which is convenient. Because arrays, like if we're deleting a child, then we know that's going to be valid. We don't have to check that someone's like, I don't know, inserting an object straight into something straight into an object. So hold on, oh, of course it won't compile. Okay, I'm just gonna children. Okay, so we now should have this code. Oh, which Russ is complaining about? Oh yeah, okay. So we haven't actually made, or we haven't told Rust that delete error is an error type. We just created it, and what we're going to end up with is, you know what? I'm going to refactor this anyway. So we only inserting the only possible problem is a fixed child count. That will change. I think with some refactoring, we'll end up doing that. But the specific case now is that if the number of children is 0, then we want to display this error message as we did before. Otherwise, we just return. We return the message we had before, which is that it can only have so many children. And I suppose we ought to make a special case for 1, but this is a debug message. So we just want to say, instead of node cannot contain 0 children, can only have 0 children. That's a bit weird. Like we should say cannot contain other nodes. You know what? I'm a pedant. I'm going to make num children equals 1, a special case, to say can only contain 1 node child, not can only have 1 child. There we go, D2FN. So now that we've refactored this, it's precisely the same for delete error, right? Because displaying a delete error, if it's fixed child count, i.e. delete error fixed child count, okay. Then if it is a fixed child count, then we just do this. Except we need to say something like node thing. We shouldn't really be able to meet this condition, because removing a child from a node that could never have children is kind of that's kind of weirdly like how does that even happen? So if we just delete this, cannot have children, but we tried to delete a child. I think that's a fairly decent description. And we say something like cannot delete from a node, and then the node name can only have 1 child. And then our message for the second step is essentially the same. Ooh, that's spicy. Right, except that we need to say so many children. And I believe the others had a full stop, so we also do that. The only thing that we also have is the index out of range. We need to find an error message for that. And it's node num children index, I believe. And we write f to remove child number. Oh, nice. I think someone has set the fire alarm off. Okay, that normally happens. We have a really trigger happy fire alarm in the kitchen. So that's gonna happen. So we try to remove child number thing from the name, which only has the number of children. I'm not going to case match this time. Consistency is not happening right now. Num children and node. Oops, and we need to return. Okay, so that's happy, and now we just need to implement error, which the error doesn't require us to do anything. It just requires display to be implemented, and we've already done that. So we should be able to say this for delete error and nothing. I believe you can do this. No. Debug. Oh, we didn't just derive a whole load of things. Okay. Yeah, we need to just derive the basic things like debug, clone, oops, clone, hash, eq, partial eq. Oh, interesting. Oh, we need to deref. And that will be the same error down here. Also the same error here. I expect the errors will happen down here as well. There. Okay. Okay, still not compiling. Why is this? Oh, because we deleted no possible children from insert error. So we removed no possible children from here. And then we try and construct it somewhere on line 364 according to the compiler. Oh yeah, here we go. So instead of this is fixed child count. And then the child count is just 0. Oh, okay, right. This is getting somewhere. Okay. How did I fix it elsewhere? Why? Because we're not actually mutable borrow. Oh, in order to borrow fields. So what happens if we drop fields? Oh, you can't drop the reference. Okay. That's a bit inconvenient. Maybe, but I don't want to calculate display name until it's needed. Maybe if we clone, which is kind of silly because we're creating a string and then immediate. Okay, that doesn't help. How do we tell Rust that this is okay? Is it okay? Because I think this is okay. Basically, what Rust is complaining about is that in this pattern match, basically Rust has some rules that you're not allowed to borrow. You can't have mutable access to a data structure at the same time as somewhere else having immutable access. So you could never end up in a situation where something's reading from data as it's being written to. Because if you have multiple threads involved, then that gets really messy. So the way what Rust says is you can have any number of references where you can just read, because reading as many times as you want from data is okay. But as soon as you have one reference that can be written back to the data, then you can't have any mutable. Then you can't have any other references. That has to be the sole reference to the data. And what it seems to be complaining about is that in this line, it's borrowing. It's mutably borrowing fields because we might want to edit it. But then here, in order to get the display name, we need an immutable reference, and that can't exist, which is very strange. If we underscored this, then it would probably have bigger problems. Yeah, and the type checker runs, the borrow checker runs after that. What happens if I move it out of here? What? Oh, it just wants this. And same problem. Okay. Maybe we just can't return the name. Oh, we don't really need the name anyway, actually, thinking about it. Let's just undo back to where we were. So I think this name is not essential. And we could do the same thing down here. Now if we go to here, because all we're saying is that we try to index out of the array. It doesn't really matter what the node was. from a node that only has so many children. Oh, okay. Well, so we can't run this code yet because the code is not used anywhere. But it looks like deleting children is a thing. So we now need to finish this function so that it actually works. What we've got now is we've cloned the parent. We know which index the sibling is on. So now we want to delete it. So we say clone parent dot remove child and then at the cursor sibling index. And we have to use this. So we're going to just return. And then we're going to say this is a result of something and then self dot node. Do we not know what things? Oh, is it just node? No, a node is a type. Oops, node dot delete error. Oh yeah, okay. So the question mark is just saying that if this returns an error, then just return straight out of the function with an error, and clear up the data as well. Once we do this, we need to just finish the edit. We call that a helper function that just like stitches the tree back up. And we want to go to it through nodes.clone, nodes to clone, and the cloned parent is the thing node we want at the bottom of that edit. And then once we've finished, we just return OK. Okay, and now we don't get any warnings because Rust can't see that, like, Rust thinks that our thing could be a library, so this public function, even though it's never used anywhere, it won't trigger a warning. However, we will just implement delete here, insert child, insert next to child. We want another change here, function here, because this is where all of the editor level functions reside. This is some horrible code that I'm going to replace, or if someone wants to keep on the idiomatifying, I don't know, making the code more idiomatic. This could do with being fixed. I'll make an issue if anyone's interested in doing that. Then make an issue and I'll explain. Because I think there's a way of making this much easier, which is that we've essentially just got an error type, right? And we could just do this as an error type and then push the problem lower down, because we can kill two birds with one stone. Yeah, random aside. So we want to remove the current cursor. In fact, I've just realized there's going to be something strange. There's going to be some undefined behavior. If we delete a node that's at the end of a list, we need to update the... so let's say we're deleting the last child. Will this run? I think it will. Yeah. So let's say we get to the... we add an array. And let's say we want to delete this, which is not implemented yet. But let's say we do want to do that. And what could potentially happen if we didn't update the cursor index is that the cursor, we don't store a pointer to the cursor. Instead, we have a list of which child indexes there are. So the root, there's always one root. So root, we don't have to store anything. And then for here, we say this is the 0th, this is the 2nd, this is the 0th, the 1st, the 2nd, and the 3rd. So our path is just 3. But then when we delete it, then what do? Is so we go to the root. The cursor is the 3rd child of the root. Well, that's 0, 1, 2. Where's 3? So we need to move the cursor up by 1, if it's possible. Yeah. So before finishing the edit, it doesn't really matter. But finish edit, I think we should do it before that, because I think finish edit captures the cursor location. So we need to do this. So just before, let's comment this. So say finish the edit and commit the new tree to the arena. And here we move the cursor up to its previous sibling if one exists. So therefore what we're kind of saying is if cursor sibling index if cursor sibling index is 0, then we can't move back, because doing so would cause an overflow. We would go into negative numbers, but the numbers are unsigned, so that would it would cause Rust to crash actually. But in some languages like C, it would just let you do that, and all hell would break loose. So what we need to do is we need to say, oh well, if we can't do that, if we can't move back a step, then we need to move up instead. Because we're deleting the last child. We need to do something. Maybe we could do something slightly more intelligent than this, which is to say, instead of this, if the clone parent dot children dot length, if the length of this is now 0, i.e., so we finish the nodes. If we remove the last node of the only child of a node, then we move the cursor up. Oh, thank you, Rust, for reformatting my code when I didn't want you to. So therefore, self.current cursor path dot pop. And we know this is valid because if we were trying to edit the root, or this should say can't remove, trying to remove the root. And if we okay, so if we're not the last child, then we still need to check that, sorry, if it's not the only child, then we still need to check that it is in fact the last child. So if cursor sibling index is the same as the new length, clone parent dot children dot length, if these are the same, then we have to move back a step. If we deleted the last, like this is the last now, the last child of a node, we move the cursor back. All right, so specifically we've now checked, and this isn't the last node, last child. We move the cursor back by 1. And that's just self.current cursor path dot last mute minus equals 1, and we're going to have to dereference that. What? Oh, last mute unwrap. And we should probably say we can unwrap here because we know we aren't removing the root. Because the root has to exist. You can't have a tree with no root. That doesn't make sense. Okay, so this code still never gets called because we don't have delete cursor yet. Mute self. And we don't even need any more arguments actually, because I'm fairly sure editable tree mod. What's this function called? Oh yeah, it's just delete cursor. So we literally just forward delete cursor. Oh wait, this self.tree delete cursor, and then if we have some error, so if this returns some error, then we need to log a warning. Warn error. So this is the format that I'd like this to end up as, because this could just all of these like crazy branches of like if some situation is not valid, then we should wrap all of these cases. These three cases should just be error types returned by the tree. So somewhere deep in here. Oh yeah, here is the function we're actually calling, and this should return a more complicated error class. Sorry, not class, data structure. So where's delete cursor? Well, where is this used? So it's used here in this big match, and what we'd like is a case. We need a new thing for delete, which has no arguments, and then literally all we do is self.delete cursor. And it's telling us that this is not defined, which is, yes, it isn't defined. That's correct. So, ooh, how did this end up above current node? Oh, after the cursor. Yeah. Okay, so move the node under the cursor. Just delete. Now this will probably complain. Where is this? In the description and color. Oh right, we need action delete, and then it says delete cursor. And we don't have a thing for this. Color delete can be just normal red, I think. Okay, so it's saying we don't have a thing. So we never construct delete, which it is completely valid. What we need to do. So we also have we have a thing for commands as well. Sorry, a data structure for commands, which are kind of the same thing but without any arguments. And the intuition behind that is that a command are the things that key bindings bind to. So for example, Q is bound to the command quit, or I is bound to insert child. And it doesn't matter if there aren't any arguments to that. Like there can't be any arguments to that, because if there were any arguments, then they would be multiple keys, so they can't be bound to directly. So delete the cursor, and this is just going to be called delete. Now we need an extra match here for delete, and it's just going to say delete. And now the key bindings, we need a binding for this, so D goes to command delete, and where's the... Oh, there's parse command that converts... oh yeah, some delete, that's nice. So this converts a sequence of characters into an action, with the intermediate step of first converting the first character into a command. So we need some command delete, and then this has nothing, so we're just going to immediately return some. So some refactoring has been done to make this nicer. Oh, it's action, isn't it? Okay, so I think this should be enough. We should be able to... Oh my... That actually worked. Whoa. Insane. Oh my word. Okay. Okay, let's a few things. If we delete the root, it crashes. Okay, I think there's just a panic there. The same as if we insert... Oh, yeah, so if we... if we insert a hold on, what's going on? Okay, never mind. Deleting the cursor, the root crashes. I believe there's just a panic in there somewhere that will... it's just... yeah, it was just a kind of to-do. Let's make the code crash, because crashing is safe. It's generally speaking bad, but it is at least safe. You can't have some weird undefined behavior happen if your code just crashes. So that's, I believe that's deleting done. Ideally we'd actually, oh, here's the panic. Here's the panic. So this is what's happening. I believe if we yeah, if we were to remove the panic, the code wouldn't crash, but it also, like, what does it mean to remove the root? You can't really remove the root. That's like, in fact, I think it would crash later on. So the panic is, yeah, it doesn't really matter. But what we would like to do is to return a different error. I am not quite sure how to handle that, and it's about time for dinner, I think. So I'm probably going to sort of wrap it up. I'm going to commit the changes. Did that work? Can you see it? Okay. I'm just going to make commits for the changes and then call the end of the stream, I think. I believe everything... Oh, except this little thing that's make editable tree. Oops. Or dag.finish edit private. So that was one change, and then the rest of it is just implementing delete. And I believe that's just all one thing. Oh, there's the cleanup here as well. We should commit that first. So we removed some duplication, so no possible string from insert error. That wasn't directly to do with deletion. Yeah, and this is just, let's say, refactor unnecessary enums in insert error. And now everything is just implementing delete. We need a delete error. Should this be remove child or delete child? I think it should be delete. I called it delete. I called it remove to be consistent with vec remove, but it's inconsistent with the rest of the code base, and that's more important. So remove child. Now the question is, hold on, did that not even do anything? What? We need to change the chlid. No, I think not. Renaming this and then this needs to be delete child. Now the code should be back to compiling, I believe. Yeah, and do the test run. They might have broken actually. Oh no. Right, so now it should all be consistent. It should say delete child. Okay. Deleting the cursor. Nice. Okay, so I think that's everything for today. We made some progress though. So now Sapling is kind of vaguely convenient for editing the subset of JSON that we can edit. In fact, it's kind of an editor now. We can properly edit JSON if you like. So instead of JavaScript object notation, it's JavaScript array notation. Like we can only handle arrays properly, but we can actually handle arrays properly. We can delete. We can do any edit that we want now. In kind of vaguely reasonable amount of time. Because before, technically any edit was possible because you could delete everything and then rebuild the tree. But like, who's going to do that? That's not what a text editor is. So we got that working. So yes, thanks everyone for coming, and I'll probably see some of you guys next week, hopefully.